All right, ladies and gentlemen, class recording has started. Should point the microphone out towards here so it picks up things that I'm saying. Okay. Now that we've talked about all these different categories and why are these matters here, why are those matters there, right? A lot of it comes down to what are their properties. How do we describe these different types of matter so that we can categorize them as different substances? So first, we talk about intensive, or sometimes we'll refer to them as characteristic properties. If they are characteristic properties, that means that they are not going to change based on sample size. That regardless of the size of our sample, whether it's a single atom for an element, or if it's a big brick of gold, right, that you see in the movies, because I don't think any of you have ever actually seen a big brick of gold, right? Maybe you have, I don't know, but, right? Regardless of how big of a sample we have, characteristic or intensive properties always remain the same. Intensive properties, things that don't change, can be divided into two categories. Some are chemical, some are physical. We'll talk about the differences between those two right now. So first, chemical properties. Chemical properties deal with how well this substance plays with other substances. How does this substance react when placed in certain situations? How does this substance react when it interacts with other substances? So here we are talking about the ability of this material, this matter, to form compounds with other matter, chemical reactions with other matter, etc., etc. So chemical properties depend on a substance's interaction with other substances. How well does it play nicely with other things? The one thing that we look for I don't know if we look for it, but it's sort of a consequence of checking a chemical property, is that when you look for the chemical properties, it is required that that substance changes over the course of checking that chemical property. Because chemical properties deal with how well or how it interacts with other substances. So you're going to make a new substance. You're going to change the chemical composition. You're going to make a compound or whatever it might be. Or this compound will react with another compound. It has to be different than what you started with. Two chemical properties that we look at: flammability and reactivity. Reactivity is sort of a general term that deals with that substance's ability to react with other elements. Does it form compounds? Does it do chemical reactions with other things? Flammability is generally its ability to engage in a combustion reaction. Right? We talked about combustion reaction last chapter, right? How well does it react with oxygen? And will that, create a exothermic reaction that gives off energy, that gives off light and heat, etc., etc. All right, good there? Next, physical properties. So here we're talking about characteristics of the substance that do not result in a change in that substance. So now we're not talking about its ability to relate to other chemicals or react with other chemicals. We're just looking at the characteristics of that substance on its own. Oh, good there. So here, we're not changing the substance in order to measure or to examine the physical properties of a substance. We're just looking at the characteristics of that substance on its own. Here is a list of 7 physical properties. These are not the only 7 physical properties that we may measure or look at when examining a material, but these are 7 that are pretty common and, in all fairness, pretty easy to measure about an object. I won't hold you responsible necessarily for all of them, but you should at least know the list. Some you probably could figure out on your own. Okay? I'm assuming that all of you are pretty familiar with density. From what I understand, last year you guys spent some time talking about density. Is that correct? what density is and how it's measured and what it relates. A couple on that list you probably could figure out on your own. Melting point, boiling point, duh, all right, I think you probably know those. Conductivity, its ability to conduct electricity. Generally, things that are good conductors of electricity are also good conductors of heat, right? Those are both types of energy. Hardness, that's kind of a duh as well. Solubility is a substance's ability to dissolve in something else. Apparently one line is on the next page also. That's good work on part. So, a couple things like viscosity and malleability and ductility, those are other physical properties. You don't need to change them. Viscosity is kind of a measure of how thick something is. By definition, it's actually how easy it is to flow from one place to another. So ketchup is a very viscous material because it's kind of hard to get it to move from one place to another, right? But things like water, not so viscous because they're rather easy to flow from one place to another. Malleability and ductility, these are generally properties that we associate with metals, and that's ability for us to make wires or to make sheets of those metals, how easy it is or hard it is to do that. Other than knowing what the definition are of those things, that's pretty much about as far as I want you to take it with those properties. Okay? Except, well, we'll talk about melting point and boiling point in the next section of this unit, talk about when these changes of state occur. But for now, just to review quickly, like I said, I know that most of you have done density before, but let's review. Okay. So density, by definition, is the amount of mass per unit volume. So we're looking at how crowded is this substance? How filled up with material is this material? How much stuff is there in this space? Right now, there are 20 of you in this room, right? But let's say for some reason, let's say that there was a wellness day presentation or something like that, and you guys missed class, but somehow, some way, we could arrange that both you and my third period class would come together for one super lesson, okay? But I only have this much room for you guys to use. If I had to fit 2 classes of kids in one classroom, the density of students in that classroom increases, right? Because there's more students in the same space. And that's what density tells us. How much stuff is there in a specific space? Density is defined as taking the mass of whatever substance we have and dividing it by the volume of that substance. And I believe last year, from what I understand, did you guys measure this experimentally different ways? If I say water displacement, you guys know what I'm talking about, right? You know, we can talk about how high the level of the water goes up and stuff like that. I won't make you do a lab like that. From my understanding, you did that lab last year. There may be situations where we have to measure the density of a substance, but I'm not going to do a lab strictly devoted to that measurement, because from what I understand, you guys did do that. But more importantly is, what do the differences in density do? So this picture here is a picture called a density column. It's just a beaker that is filled with different materials, but each of those materials has a different density. And as you can see from the density column, those materials will separate themselves out based on their densities. Air on the top, steel on the bottom. The liquids all kind of separate themselves out here. If you notice the trend, right, what are we seeing about densities of materials at the top of the density column versus density of materials at the bottom of the density column? Where are the high density things, top or bottom? On the bottom. Things with higher densities will sink Things with lower densities will float. The highest thing in this density, the top of the density column is filled with air. Let's say we take a straw into the density column and we start blowing bubbles through the straw. Where do those bubbles always go? They all go where? They go up, right? Why? Because air, being a gas, pretty much has the lowest density of anything that we could think of, at least here on Earth, right? Most gases pretty much have the same density, whether it's air or something else. But that's why bubbles always float to the top, because they have a lower density than whatever they're in, whether that be water or whether it be something else. Now, if we trap an air bubble in like a solid, which sometimes happens, right? If you've ever, like if you have Play-Doh or something like that, sometimes there's air bubbles that get stuck in Play-Doh or silly putty or something like that. They can be trapped for a while, but if we let them go for a while, you'll see that those air bubbles will work their way out of that material and work their way to the top. We might be able to trap them for a little while. That kind of depends on the substance that they're trapped in. We could, in theory, trap something within a solid, right, and it won't float. That's not necessarily because its density is different, but because that solid isn't letting it go anywhere. Okay, so don't think that bubbles always go to the top. Sometimes we can trap them just based on how solid something is or something like that. Okay? But this is the same basis of something like a lava lamp or something that you might have in your refrigerator at home, Italian dressing. Okay? Italian dressing is vinegar and oil, right? So oil's up here, vinegar is basically water, so because those two things are different, they'll separate out. If we shake them up, right, for a while they get mixed, but if you put it back in the fridge and let it sit there for 10 minutes, it'll separate itself back out, because those materials have different densities. Right? Wood's up here at the top. Wood has a relatively low density. If you go to the lake, right, you'll see the driftwood is sort of floating on the top of the lake because it has a lower density than water, so it floats up to the top. But if you throw a rock in, right, rocks sink to the bottom. Why? They have a greater density than other things. The difference between the densities of these materials determines how quickly they separate. Rocks sink to the bottom real fast because their density is much higher than water, right? But if you look at corn oil, which is vegetable oil, right, and water, their densities aren't really all that different. So it takes them a while to sort of separate out from one another. Good there. And in the course of talking, we discussed this. Less dense materials move to the top, more dense materials move to the bottom. Right? We talked about that. All right, why do we need to identify the properties that exist in these materials? So, especially intensive properties or characteristic properties. What can we do with these intensive properties? Well, one, we can identify a substance. Why? Because each set or each pure substance has a unique set of properties. They may share certain properties, but when it comes down to it, each pure substance has to be different from every other pure substance. Second, we can choose a substance for a specific purpose. If we're trying to make a boat that needs to float in water, right, our boat better have a density that is lower than water's density, or else it won't float. Second, we can separate mixtures. Different properties means that substances will behave differently in different situations. We gave you an example of separating substances based on density. We might also separate substance based on, let's say, boiling point. If we know that we have two substances that are mixed together, and one boils at 100 degrees Celsius, and one boils at 110 degrees Celsius, if we heat up our mixture to 105, half of it will boil and half of it won't, because they have different properties. So we can use those properties to separate things if we need to for whatever reason. right. Good there? The last part that we talk about in properties, up until this point we have talked about intensive or characteristic properties. But there are other things that we might want to know about a substance that don't necessarily relate to that specific substance. We refer to those as extensive properties. Extensive properties depend on how much of that substance is there. For instance, this balloon is filled with helium. And we know that helium has a lighter density than air. How do we know that? Because which way do helium-filled balloons go? Up, right? So helium has a lower density than air does. But we can also talk about how much helium goes in that balloon, right? It's a certain, 2 liters of helium go into that balloon. We wouldn't use that 2-liter measurement to identify the gas in that balloon as helium, because we may have balloons that have other volumes other than 2 liters, right? Or we could have other gases that have 2 liters of volume, right? These are things like mass and volume and temperature, stuff that we could measure about any substance. It's not specific to that, that material. So extensive properties, they depend on the amount or the condition that substance is in, but are not necessarily specific to that substance. Not that they aren't important, sometimes we need to know those things, but we wouldn't necessarily use them to identify something because they're not specific to that substance. All right, good there? All right. Never mind. Let's go here. Changes. I'm assuming that you guys have been introduced to the idea of physical change and chemical change somewhere along the way. And in this class, we've talked about chemical changes, right? We've talked about making a new substance in a different kind of reaction, whether that be a synthesis or a single replacement or wherever that might be. But just to review a couple of things. Let's go here. First, physical changes. The properties of the substance change, but the composition of that substance does not. Easiest type of physical change we can talk about is a phase change, where something may go from being a liquid to being a gas, but that doesn't mean we've made something new. The properties of that substance have changed, right? When we boil water, first we change its temperature, second we change its volume, third we change its density, right? But those are all extensive properties, right? Not things we would use to identify. If we looked at the composition of water, whether it's in a liquid phase or a gas phase, it's still H2O. Right? We haven't changed that, and that's the gist of a physical change. Other physical changes might be things like cutting a piece of paper in half, or sawing a log in half, or taking a spoonful of sugar out of the sugar bowl. We've caused changes to the properties of that material, namely how much there is, right? But we haven't really changed what it is. The other type of change we talk more about are chemical changes, right? And chemical changes are something that we have talked about pretty extensively in the last unit, dealing with chemical reactions, right? Substance reacts with another substance, and one or more new substances are formed. The new substance has a different set of properties than the original substance. And earlier in the period, we talked about that is one of the characteristics of making a compound, right? We take two things and we make something new, something that has a different set of properties. The next part of your outline, letter B, you probably could start filling in on your own, because we've talked about these indicators. What are some of the things we look for when we're identifying a chemical reaction? Andy, what's one thing?
Color.
Color change, right? That's one indicator that a chemical reaction has occurred. What are some other things that we talked about? Eris? Solubility, we're not really making anything new, right? We're just dissolving something into something else, right? So that's more of a physical change, because we haven't created something new, right? I think you might be going somewhere else with that, but save that for now. Andy, what's another one?
Gas production.
Gas production, right? Production of a gas. Bubbles mean that generally we're making something new. Not always, right? But it can indicate that. Nick? Precipitate, right? Eris, that might be kind of where you're going, right? That now, Eris, the precipitate part is not necessarily, we wouldn't explain it necessarily as, okay, I see where you're going with that. Because yeah, the new substance isn't soluble, whereas the previous substances were. So formation of the precipitate, right? And then the last thing that we look for?
Heat.
Heat or
Thermal energy or just a release of
we
energy.
could go, it doesn't necessarily have to be thermal energy, it could be any kind of energy, right? So it could be light as well, right? Energy given off in the form of heat or light. And we did lab 2 weeks ago, I guess, where we saw examples of all of those things, right? We saw chemical reactions occur. They gave us examples of all of those things, knowing that something change happened. All right, to finish this up, conservation. Conservation is an idea that we've talked about before, right? The amount of a substance must remain the same during a process. Now, when it says with the amount of a substance, that depends on what kind of substance we're talking about. We've talked about 2 conservation laws so far this year. Do you remember what the 2 conservation laws are? Mark, go ahead.
Conservation of
Mass and energy, right? Mass and energy are 2 conserved quantities. And that means that whatever is there at the beginning has to be there at the end. It might look a little different, but all the mass we start with has to be there at the end. All of the energy we start with has to be there at the end, right? That's the idea of conservation. And specifically for this section, right, we focus on conservation of mass. And like, the description says, the total amount of mass present before a chemical reaction must be the same as the mass present after the chemical reaction. No change in the amount of mass. Now, that doesn't mean that there isn't any change. It just means that we're rearranging stuff that's already there. We've used this idea to help us do what in the last chapter? We said something from the last chapter is based off of this idea of conservation of mass. Balancing equations is based off of this idea. If there are atoms at the beginning, they have to be there at the end. They have to be accounted for because we cannot create or destroy mass. Good there? A lot of the stuff today, right, things we've talked about before, things we've encountered before. Quiz tomorrow, open note, use the outlines we've talked about. If you have any homework or anything, use that as well.